Hello everyone, welcome back to Dragonfly Engineering. So this week we've got an interesting treat in that one of my customers allowed me to show his mold on YouTube. So this is a mold here. It's a steel mold that is probably about 20 years old, and it molds these plastic parts which you see right here. I can't get into much detail about what these do or anything, but he did give me permission to show the parts in the mold. So we're going to focus mostly on this mold. And what we are doing is a periodic maintenance on the mold itself. This mold is probably about 20 years old, and I don't think it's ever been opened up to clean it or deal with some of the defects that I was getting on the plastic parts. One of which was I was getting some flash that was forming on a smooth cosmetic wall of the part, and that resulted in kind of a slowdown in labor because I'd have to basically scrape the flash off of the side of the customer's product every time, you know, and that means human interaction, and it just slows everything down. So we had to fix that. The other thing is that there was a coolant leak that was occurring inside of the mold. And these parts have a post-process where paint or ink is applied. So having basically a tiny smudge of a emulsion oil, which is what I use, basically old machining oil I run through this mold. Well, that slight little deposition of just enough of an oil film caused problems with printing onto the part after molding occurred. So, and it was a discoloration on the surface, so it was just a hassle. The other thing with having a coolant leak in your mold is that every time a new shot of plastic goes into the mold, which is, you know, 450 to 500 degrees Fahrenheit, in this case it's polycarbonate, so it's 475 Fahrenheit, that little deposition of liquid inside of your mold cavity causes a flash steam explosion, and that affects the surface finish of the polished surface of the plastic part as well. So anyway, that both of those three problems, the flash, the bad finish from a steam explosion, and then the residual oil contamination from the emulsion oil and the coolant, which is a water-soluble machining oil coolant, was enough for us to decide to open up this 20-year-old mold and discover what our problems are. So we are going to zoom in on that and take a look. All right, so this is a pocket where we pulled a big steel core out of this mold, and this profile is the inside profile of the plastic part right here. So this guy, so basically this part ejects off of this core, and there's actually a coolant line that goes in this core, comes up and then back out, because with polycarbonates it's such a high temperature and this core is kind of a deep draw. What happens is this steel core retains a lot of heat, and the polycarbonate that's in contact with this inner surface basically can't cool off enough for the part to eject without having like tearing and galling, or basically plastic deformation and kind of a tearing effect, or basically the plastic inside is not solidified enough, and it actually kind of stretches and tears out of the inside, and you get a bunch of defects in here and actually leaks. So we definitely need to cool this off. But with the coolant leak that we were seeing, and again, this is before we opened the mold up, I attempted to fix the coolant leak by actually piping yellow paint into all of the active coolant lines, and try to do like a radiator stop leak effect, which did not solve the problem. In fact, this yellow paint coating that you can see here wound up diminishing the cooling time for this core. So actually the cycle time to mold one of those parts almost doubled because I added paint inside of the coolant channel inside of here, which reduced its heat transfer ability, and thus it took longer for this core to cool enough for the plastic to be solid enough to eject off without the plastic tearing and getting deformed as it ejects off of this core. So one of the first things we need to do is actually set up this pump here. This is a sump pump, and I've already got some tubing connected. Oh, yeah, and basically down here is the fluid intake, and this pump shaft is designed to basically sit inside of a container, which is right here. And we are going to pump acetone through this cooling circuit and try to dissolve some of this enamel paint, this yellow paint, and improve the cooling efficiency of this mold core. So that's one of the steps that we're going to do. The rest of the core that was slid in here is actually in this tank of acetone right now. So we can pull that out. Oh, and back here is the ejector pin. Here, let me adjust the camera. So back here is the ejector pin array, or the ejector plate. And then behind the ejector plate is the A side of the mold, way back here. But most of the work is going to be on fixing the issues with the B side, those three that I talked about. All right, so what I'm going to do is pull out the mold core that's been soaking in this acetone for about a week. And this acetone actually was used to clean out the gas tank on the Volkswagen thing. This car right here. And so it's got some dissolved gasoline and other funk in it, but which is also a good solvent to get rid of paint. Anyway, so we'll pull this mold core out of here. There we go. I might as well just put this pump into the tank to cycle acetone. Now there's a bunch of cross-drilled holes in this mold core. You can see all these brass plugs. So there's kind of a labyrinth of cooling lines, and a lot of times you drill through and then you pipe tap or thread the ends of your lines and then put plugs in to create your labyrinth of cooling lines. And whoever originally made this mold, they didn't quite tap their pipe plugs, their tapered pipe plugs deep enough, so they wound up grinding off the tops of these plugs, and some of them are actually stripped, like this one. So we're not going to open these up because it's probably going to be more trouble than it's worth. But yeah, because some of these are ground down so far that whoever worked on this before just stripped out the hex head. Scotch-Brite pad here, and I see like basically baked on old oil and things on the outer walls of this this mold insert. Now it took me and my customer, maybe an hour or so to basically knock this steel core out of the frame of the mold, just because all of this old grime had basically baked on over the last 20 years and pretty much glued in the entire mold core into the mold base, just from, you know, an old coolant leak that basically just kept dumping out more and more and then baking it on, because again this mold operates at about 100 degrees Celsius or 212 degrees Fahrenheit, and with a slow leak it just slowly accumulates this kind of this sticky crust film that glued the insert into the main body. Now this is Brillo, so I'm not going to actually use it on the polished mold surface, but around the parting line and the back of this insert I can clean it up. I think the source of the flash that we were seeing, again the flash is basically a gap in the mold that plastic can squirt into, was probably due to the buildup of this this film and contamination on the parting line of this mold block to the actual core, or to the base of the mold body itself. I did notice that the bolts that were holding this mold insert into the main mold body were not very tight over the 20 years of operation. So with loose bolts, I think this mold block slowly worked its way forward as a film of crud slowly built up, and that change in dimension caused enough of a whisper of a gap that like, I don't know, 50 microns or 2 or 3 thousandths of plastic actually shot into the gap that was created, and thus caused the flash. So we're going to get rid of all of this kind of contamination on the back of the mold so that we have a true fitting of this precision mold block into its cavity. And hopefully we'll get rid of that basically paper thin flash that we were getting in the part. And I'm just dipping into this old acetone as a general solvent to clean up our interface of this mold block. The most likely cause of the leak that I was talking about is actually a bad pipe fitting in this mold block, which, you know, screws into the side like this. But we'll find out. And I'm showing the mold maintenance on this mold because I'm going to load it into the dual shot molding machine pretty soon, like this week, as well as a in-house product mold, which is yet another customer's mold that was actually scrapped to me. So they no longer needed the part. And I'm going to repurpose the part that the second mold, which we'll show probably next week, will be used for basically a tray that would hold end mills or brushes or markers or pencils. So we'll take a look at that here in a little bit. But first, we need to focus on getting this mold ready because I have an order for more of these parts coming up. So the thought is we're going to mold this part on the first injection unit side of the dual shot molding machine, and then the second injection side will house the my in-house part, which is going to be a repurposed old customer mold. So we're going to have two products molding at the same time on the dual shot molding machine, with actually two different materials. This is polycarbonate, but the other part is going to be polypropylene. So that'll be pretty fun to see. So the next episode, you're probably going to see me retrofitting that other mold, and we'll have a dual shot operation and a subsequent video after that. Now there are some components in this mold which have been basically decommissioned. So these side poles here and this feature are not actually molded anymore. So at some point in the history of this mold, the part that was molded with these two side poles was capped off by the runner. So it's no longer actually molding that part. But we still have to have these cam actuated side poles function because they're integral in the mold itself. So I'm not too worried about this part as far as defects, but we still got to clean up around it so that it actually still opens and closes as the mold or the family mold opens and closes. I can see old surface grinder patterns on this mold where people had dialed it in or done modifications to optimize this product. And of course this is done by someone probably overseas long before I ever got my hands on this. So what I'm doing is just cleaning, preventative maintenance of the mold so we can get better parts coming off of it. And then I can clean out the polished area, even though technically paper towels do have a slight abrasive effect to them. I think we'll be okay with my gentle cleaning here with IPA. I can also see some die grinding marks where whoever originally made this mold had to do some field modifications with some die grinding passes to add radius on these corners so that this block would fit into the cavity itself. Okay, and then looking at the bottom, we'll make sure any kind of crud in this parting surface is cleaned up. Because basically any kind of little layers of crud can add a thousandths or half a thousandths. And when you get a few of those stacked up, you wind up with basically a sheet of paper's worth of of potential flash in your part. So we can set the pump up to pump acetone through this core. And you can probably surmise how this goes back together. So this mold insert gets up into this hole, and then this core actually is in the middle of this profile right here. So I'll move this aside because we do need to do like a deeper cleaning of this whole mold cavity. Yeah, because more of that crust is in here. We did like just a quick pass cleaning, mostly so we could slide that block out of here. But I need to do a deeper clean of this entire surface without affecting the mirror finish of this mold core. And since I'm working with acetone, I usually like to put gloves on, because acetone is a pretty aggressive solvent, and it can actually, I believe it can actually pass through latex or nitrile gloves, but it can also pass through your skin a little easier and then leave whatever it was carrying inside of your body, supposedly. So yeah, try to wear gloves when you're messing with acetone or more aggressive solvents. And then the more important is to clean all of the films of caramelized coolant off of the bottom surface of this mold base, so that we can close up whatever gap we had that was causing that flash that I had mentioned. Yeah, so this is our flash issue right there, which winds up being basically down in here, which involves this, the other mold block. Basically right here. And I don't really see any defects other than the fact that we're cleaning all of the crap off of this surface and this surface. So hopefully we'll close that off, and then our little flash issue that we were getting in this area will just go away. Hopefully, I don't know if this is a spark-proof pump, but I am taking a little bit of a risk that this whole thing turns into a column of fire when I turn that pump on. But I'll be here, and I can always actually have the fire extinguisher handy, so that's always a good thing to have. But yeah, we got to clean out the yellow paint in this circuit right here. So I am going to take a couple of these nipples, which are stock with the this mold. This is the mold insert. I guess this is a mold insert that houses that mold core, and this threaded nipple with the fluid disconnect on the end is actually threading into this block, this mold insert, to run coolant up and up into that core and then back out through this port right here. So getting rid of the yellow paint that we put through this mold core is the next step here. So I'll get the socket wrench to screw this one in. We've got our return circuit here. And then this will dump the acetone back in the tank. And these they're like air connections. You just pull back the ring and push and connect. And I hope these are rated for acetone, but we'll find out. Okay, the big question is, will this motor create sparks when I turn it on and blow up the entire shop? There's only one way to find out. Okay, I'm going to plug it in. Okay, well, so far so good. Make sure we're actually pumping. And we are. Pretty good flow, actually. Of course, this is something I don't want to mess with. I mean, one thought is if you cover this up, you increase the concentration of acetone vapor to the point where it finds an ignition point. So we could just be below the vapor ignition point right now. But anyway, So I'm going to run this acetone through here, and I will look for any kind of leaks. I don't see anything leaking out. All right, so looking inside of here, we're running that acetone right now, and I don't see any issues in the mold. I see a few spots that still need some cleanup, like right there. I can zoom in on that. Little crud right there. A little bit around here. You can definitely see that this mold has had a long, interesting life. You can see some ejector pins were sort of drilled into the back of this thing, and here we got some stuff going on and a few dents that look like there was some work done on it, like that dent right there. So anyway, yeah, this mold still makes good parts. It's just other than what we're trying to fix today. So I may run this acetone through this mold core for maybe like half an hour or so. Yeah, there's another dent. So this mold's been apart a few times. All sorts of stuff in here. So any of these dents or just the accumulation of that crud would have caused the offset in the mold block, which would have caused our flash issue. Someone scratched the center there. I wonder what that's all about. It's almost like someone scratched a center line. Oh, and I got a plastic pellet right there. I think that's, oh, that pellet's been there a long time because I'm doing white now and that's gray. Huh. Anyway. Well, yeah, so we'll be back once this acetone runs through there a while. Yeah. I don't see any yellow paint coming out yet. Maybe we won't. I may have to hit it with the compressed air or something to clean it out better. Maybe it's completely dissolved, but we'll see what happens here. I do have this brass brush to hit any of those last grimy caramelized spots. Actually, I'm going to clean out all the sharp corners of this pocket too, with the brass bristles on the end of this brush. Usually brass doesn't affect steel parts, but you still want to be careful that you're not going to damage surface finishes or mirror finishes. So kind of do a test pass and then look to make sure you're not screwing up everything. But I've already done that on this one. And then there's kind of like cooked on white film on the end of this, which again, this isn't a parting surface, it's the bottom of the chamber. So I'm gonna see about cleaning that off too. It could just be baked on from the white color concentrate that I'm using. I may actually get a stone and see if any of these dents have a raised up berm on them. This handled diamond hone, so this is diamond grit on a plastic handle. This is a coarse one. It may be a little too tall of a handle, but I could probably get to some areas and look to see if there's any high spots I can knock down. Doesn't look like it, at least there. Diamonds are pretty aggressive abrasives. They will take off some material. But here we're just kind of looking to knock off any high spots that we see. So I'm looking for a uniform scratch, basically. And I don't see any issues. This little insert is a little bit high, but it could be that it's supposed to be slightly high too. The alternative is to use an actual stone, and this will polish high spots around dents. Like that one right there. Of course, you probably can't see it from way back there. Yeah, so there you can, by using the this style stone, kind of like a traditional actual stone instead of a diamond tool like this one, you can actually halo your dents by seeing the shiny ring around it. So that one right in the middle, you can see is a fresh dent or a dent that no one ever fixed. But you can see how the diamond tool kind of just blasted over everything and scratched up the whole surface. So yeah, using the true stone will basically put a mirror finish around your high spots from dents. Because when you dent steel, the amount of material that you lost from the negative dent heaves up around like a crater. So you got to take off that crater wall around your dent, because there's conservation of mass that's still going on. Let's see what this one looks like. Yeah, that one's got a high spot around it too. You can see the shiny around it. And someone just left like a freaking tap thread chip in here when they assembled this mold, and it just pushed into the base of the mold. Let's see what else we got. You can see some of the original machining marks. Those are basically the tool flexure. That's what those lines are up there. And I'll see if I can stone and check out what's going on with this dent, if my stone fits in there. Anyway, so we'll just keep fussing over this mold insert. I still don't see much yellow paint floating in here, so I don't know. Hopefully we're doing some good by dissolving out whatever paint is in this mold core. And I'm gonna stick some of this grease down inside, probably about mid-level, because I don't want the grease to actually migrate to the bottom and then get under the block and then prevent the block from pushing all the way down. Because grease, when it spreads out over a large area, it creates a huge amount of back force, and you can never really get down to where you need to be, because the layer of grease, viscosity times 15 microns is like tons of force to actually seat the block completely. So we want to keep grease off the bottom, but I do want to lube the block as it goes in. And I also want to put like a water seal basically around our fluid ports to help prevent any liquid from poorly connected nipples to get down to contamination spots on the actual mold itself. And yeah, probably about right here, we'll do like a grease layer all the way around. And this to help us just slide the thing in, and it's also kind of like the equivalent of anti-seize. So having grease in your parting line helps with pulling this mold core out in the future as well. And it keeps the caramelized, baked on coolant residue from from basically gluing this mold core into the mold base itself, like we had the problem trying to pull this thing out. It was a lot of hammering and heat for like probably an hour to get this block out of here, because it didn't have like a anti-seize type grease perimeter around it. So since I'm putting more grease on the block than in the cavity, it's naturally going to get scraped up to the surface instead of pushed down into the bottom where we don't want the grease because of dimensional concerns or assembly tolerance concerns. But I don't really have access to the bottom of the block, so I'm going to put a little bit of grease on the bottom floor here, which basically has no features anyway. Okay, I think we are ready to put our mold block back into our mold base after a pretty good amount of cleaning that I did. You got to get this thing as parallel as possible when you start it. There we go. Okay, that was it. You can see we scraped our grease forward, except for down here, but I didn't put much grease down there. And then we'll wipe off the excess. So now what we're gonna do, I'm thinking we can probably finish or stop running the acetone through our mold core, this guy. If it would have dissolved something, it would have done it now, or you let it run overnight, and I don't want to leave acetone in an electric motor running without supervision. So I'm gonna stop the pump now and disconnect our acetone lines. So that was actually a pretty easy fit. They must have added a few thousandths of clearance for this block to fit into the pocket. But the grease that I added also helped kind of keep the spacing equal, because the high viscosity will help to normalize the forces so that you don't jam, you don't angle lock the block as it's pushing into the mold. But the grease will help keep it floating and drive it home. Until, usually after, with a mold insert, if you make it 50% of the way in, then the geometry will allow you to just stay parallel and go all the way in. Oh. So I am going to give it a WD-40 kind of coating in the back, and then we're going to hit it with that same Brillo that we used with the acetone, just to try to get some of this rust and cosmetic issues out of here. So these bolts basically pull that mold block that we just pushed in. It clamps it home. And these are the ones that were loose when I loosened this up, which means that the mold block wasn't fully pulled back. So that's probably a maintenance item that I need to watch a little closer. So this is where we're drawing that mold block to the new correct position, where we won't have like 100 microns or 4 thousandths of caramelized grime that we're actually seating on, but we're doing a steel to steel original fit now. I don't really have a torque wrench per se, but I am tightening these up pretty good. And this mold probably weighs 1,000 pounds as well. Okay, anyway, there's our mold block reinserted, hopefully without leaks. Okay, so we did have to pull the ejector plate out of the back of this mold, which is always a little problematic because getting all of the ejector pins to line up perfectly with their holes can be a problem. So a lot of times you actually have to disassemble the clamping plate, which is this back plate, which pinches all of these ejector pins, these really long ejector pins in place, and string each pin in with the plate and the bearing rods all the way forward. So you do one pin at a time, but trying to get, I don't know, 20 pins to line up to all of their holes simultaneously is difficult. But before we do that, we got to clean these pins anyway. There's old grease and grime on them. And hopefully no galling effects. And I'll probably just hit these with WD-40. I believe there's like specialty ejector pin solvents and lubes that you can do, but I typically just do WD-40, just a thin oil to help keep it moving along and not starting a galling nucleation point. And some of these are actually tubes. There's all sorts of crazy stuff going on with this mold. So these are actually guide tubes for some static pins that are actually in the mold base in the back here, which is off camera. But we'll take a look at that here in a bit. Some of these have stains, like rust stains, not necessarily residue. But if you've got residual crap on these pins, they can start to cause you problems by causing the steel to gall up, because some of this plastic residue turns into just hard carbon, and then that hard carbon starts scratching the steel, and then the steel starts to get a little pile of steel powder that starts to scratch more, and then it turns into a little ball of steel, and then that little ball is digging in, and that's the beginning of galling. And eventually your pin will weld onto like a ball of steel that's gouging back and forth, and then your pin breaks off, and then you could seriously damage your mold with a pin that's stuck forward and then broken off when the return pins, which are these huge pins out here, push the plate back. But if you snap a pin in half, that ejector pin could still be forward in your mold, and then the molding machine won't know until it feels it gouging the A side or your finish cavity of your mold, and then, which sucks. So you want to keep these pins as clean as you can keep them. And I'm almost certainly going to have to unclamp the clamping plate back here to line all these up, because they're all just kind of flopping out here. But we'll see. I'll try a little bit to see if I can get them all to line up, but usually that's a fool's errand. You don't want to actually remove material on these pins, because that results in flash potentially going down your ejector pin holes if you reduce the diameter of your ejector pins too much. Okay, then we need to wipe these all down, because you don't want to have grit or abrasive get trapped in your ejector holes either, because that abrasive will just exacerbate the opening up of the tolerance of your pinhole, and probably add to a galling situation as well, with the abrasive causing the steel powder to accumulate and then gall up. All right, you can see the graphite dots in this main bearing or guide bearing, and those slowly help release powder or dry graphite lubrication for these bearing rods on the A side. And that's a bronze bushing with graphite inserts. Okay, and then these holes next to the main bearing are the guide holes for the return pins, which are basically just, the ejector plate doesn't need to be as precise as the main bearing or mold bearing guide pins. So they're just machined in. But I think I'll give them a shot of grease in that hole. Doesn't hurt to grease the main bearings too, but the graphite will keep them relatively lubed throughout their whole life. Okay, I guess I will try to align these. I got to make sure, yeah, okay. So checking the orientation. I guess I could, okay, let's see what happens. It's unlikely this is going to work. Yeah, they're already fighting me. You got to get basically all of them aligned at once. Yeah, it's not going to happen. All right. So we got to take the back plate off, the clamping plate. I'm going to check this anyway. I was 4 screws. All right. Okay, so now we'll move the ejector forward. Wow. Huh. This ejector pin had a little side pin in it for orientation. Hopefully there's not too many crazy surprises in this. All right, so I'm pushing this plate forward. This will allow me to align all of the parts easier, one at a time, that is. It's kind of, if the pins look like they're horizontal, then you're good. Because this mold went through probably a lot of changes. Okay. So if we just go fully forward, such that you see the pins poking out the front, then that will guarantee that we are long enough. So I'm just going to kind of hammer these in, and we should start to see pins come out the front, which we are. Oh, that one had some crud in it. Huh. Yeah, I see some kind of cycling these pins all the way in and out of their ejector holes. It's cleaning out some of the, scraping off some of the crap that's on the sides of these ejector pin holes. Okay, and then the best guarantee that all of your pins are in the right spot is if you can push the plate basically all the way forward like this. Because there's no way that a crooked pin is going to go all the way in this scenario. So this is like eject all the way forward, and this can also help set the location of the feet of your ejector pins too, because with zero gap at the top, these pins are as precisely aligned as they can be into their holes. So if we then clamp the mold, the ejector pin clamp plate down at this point, then if these pins are actually pinching off on the plate, then they're going to be located exactly where they need to be, coaxially with their ejector pin holes. All right, let's do this. Oh, actually this bearing stayed in the front side of the ejector plate. You can see this bearing has graphite plugs in it. So this is a self-lubricating bronze bearing. These black dots are actually graphite cylinders, and they slowly release graphite powder to create a dry lubrication for the inside against these rods back here. There we go. Okay. Another thing that's handy is to get two pry bars that are copies of each other or duplicates, and then you can stick pry bars on each side of mold components like this, and then open up components easier than trying to get a screwdriver in there or something else. You know, just two of these with equal force makes a smooth opening action on molds, especially when you're on a bench trying to open up a mold. All right, so we'll push our B side of the mold forward, and then this is our base. Again, with these long through rods, which are actually static rods, and those ejector tubes string onto these. So I do need to align these three rods to the holes in the back of this ejector plate. And like I mentioned, I'd already pre-lubed our bearing rods for the ejector plate. And then these things here, all of these they're called pedestals or pillars. I think they're called pillars actually in molds, but I interchange pedestal and pillar. But these help support the back of your mold, and there's corresponding through holes in your moving ejector plate. So basically, when you injection mold into a big mold block like this, believe it or not, this mold block can actually flex from the hydraulic force of the molten plastic being shot into the mold, because you know it can wind up being like 10 or 20,000 psi times, you know, however big your part is. That can turn into hundreds of tons of force trying to bend your mold. So these pillars, as many as you can fit into the back of your mold, helps keep the mold block from deforming and causing flash on a high pressure injection profile. So anyway, that's what these guys are, and then these are our bearings, and then these are our static rods that go into the mold cavity itself. And then these are riser blocks, left and right, which basically creates space for travel of the ejector plate that's going to wind up sitting interleaved in all of this structure. So I'll move this forward a little more. And I'm on a big welded steel bench, you know, because this mold, like I mentioned, probably weighs 1,000 pounds or so. So you need to have a bench that can withstand all of this weight. Okay, I'm going to bring this mold in, and I'm going to gently start to bump it in and aligning our static pins through the ejector plate holes so that they actually string through those ejector tubes. So I'm kind of watching and listening to hear that those pins actually engage the back sides of those ejector pin tubes. I'm just gently bumping it so that we don't overforce and buckle one of these tubes or cause a scratching or a galling effect or anything like that. But I think we're engaged pretty well. So now the next trick is that we align the guide pin that's tied to the base of the mold into the bronze bearing in the ejector plate. All right, I'll keep kind of bumping this guy in and getting the everything to line up. It looks like they lined up pretty well. So this mold's actually a pretty high precision mold. And we'll bring the bottom plate assembly home to the main block itself. And then we will tighten these bolts down, and we should be ready. Okay, let's spin this around and see what we got here. All right, so this is the front of the B side of the mold with our ejector tubes here. All the other ejector tubes are deep inside of the cavity itself, which is interesting. So I'm going to push this back so that we can test fit the A side, which is back there in the background. Let me get this pushed over on the table. Yeah, like I mentioned earlier, this ejector plate was completely seized when I first got this machine, or when I first received this mold from the customer. So I had to cycle it back and forth slowly and spray a bunch of WD-40 and other stuff in here to finally get it to start to actually cycle the ejector plate. But now it's going good. I think I was basically just rubbing on the table a little bit. It is a good idea to relieve your ejector plate, this top and bottom surface, so that you can cycle it on a table without the surface being flush and picking up high spots on the table itself. But with this rubber mallet, we can send it home. And then I see some residue of what's probably like remnant color concentrate in the plastic on the middle of this. So I'll clean this mostly with WD-40. Interesting thing though is this is, here I can zoom in. These side pulls that create some obsolete part, which is shut off in this particular mold, have angled holes and a wear plate that's angled on the back, which string onto these guide pins here and then a heel block here. So as the mold closes, these two pins go in these two holes and it pulls these two side pulls together. And then when the angle plate hits the heel block, that's when the high pressure clamping occurs, and then these pins are just waiting to open the side pulls apart when the mold opens again. Down here with this bronze piece, it works a little different. There's still some angled surfaces that these bronze pieces slide on, but it's captured inside of the backside of this mold insert, and there's a die spring that actually defaults by pushing these bronze pieces out, and when they push out, they actually cam toward each other, which relieves the undercut that's molded in. When these bronze pieces are pushed closed by these tabs being in contact with the B side, they move farther out to create the actual undercut. So they move out when the mold closes, molds an undercut, and then when the mold opens, they move together to clear the undercut, and then the part can eject out. Hopefully that made sense. So anyway, I'll do some cleaning of this surface, mostly with WD-40 and paper towels, and then we can close our mold up by lining up the guide pins to the bushings here. Now, since this bronze undercutting assembly here is spring loaded, we're not going to be able to completely close the mold unless, you know, I can push this super strong spring, which is probably 100 pounds at least, back into the mold. But what we can do is close it down to the 3/8 of an inch that is exposed here. All right, now we'll just push these two halves together. The A side of this mold does have these super long spindly pins, which are sink control. There's a couple of areas of thick plastic, so they put these pins in to core out like corners where like a radius meets with a square corner, and then there's like a thick section. So they put these round core pins in just to get that plastic out of there, so there's not as much of a sink effect when the plastic solidifies in the mold itself. So it's cosmetic, but they're really flimsy and cause of much concern to me whenever I'm running this mold, because I don't want to have to replace one. I think someone already did replace one because one is shorter than the rest in a different shape. So it's probably not that big of a deal to replace, but it's just more work I don't want to do. All right. Now we'll bring it over. This is probably 3 or 4, maybe 300 pounds. And making sure that we're keyed right. Usually one of these guide pins is offset from the rest, so you can't accidentally flip this 180 degrees and load the mold backwards, which would crash most of the delicate items of your mold itself. But I double checked that we are correct here, and it actually slides in easy. Look at that. Oh, wow, that was really easy. Let's see if it opens that easy. Yep. Okay, now if the ejector plate was forward, then the what's called the return pins would be forward, and the A side surface of the mold would actually push on this pin, which would push the ejector plate back, which would retract all the ejector pins in the cavity area. So it's a safety mechanism, this return pin here, or these 4 return pins. Let's do that again. Normally you gotta bang on this because you can get little interlocking problems, but this mold is run for 20 years. So I think it's probably loosened up where I don't get the high precision locking, where if you're not perfectly aligned, then it jams on you. Yeah, this I can wiggle this back and forth. So there is wear on this mold, but they may have made it loose from the get-go. If the alignment of the A and the B side of the mold isn't critical to the function of the part, they could have just made this loose to start with, so this process is easier than normal. But yeah, that goes in real easy. Okay, there we go. So our mold is back together, and now it's probably too heavy to slide on the table. Yep. Final thing is there's a ring of molten polycarbonate plastic on the injection port. So the hot nozzle of the molding machine comes up and then pushes up against like a hemispherical profile with a hole where the plastic squirts into the mold itself. And I've got like an old ring of polycarbonate here that I need to chip away, just so that it doesn't cause problems when this is cold. This plastic is not melted, but the hot nozzle comes in, it may rub on this and cause me issues and not have a good seal. So maybe off camera I'll chip away at this with a chisel and a hammer, but otherwise our mold is complete. So thanks for watching Dragonfly Engineering. So the next episode will be me retrofitting another former customer's mold that was abandoned or given to me, and I'm going to modify it to mold a product that Dragonfly Engineering will sell direct to customers. And that second mold will be running in the second position of the dual shot molding machine along with this mold. So 2 products will be molded at the same time. So stay tuned for the retrofit of the second mold of this little mini series, both of which will be running in the following episode after that. So I'll see you guys next week, and thanks for watching. Goodbye.